All right, thank you. It's really an honor to be here. My name is Barak, and I'm really excited to share this work with you. This work deals with two important no-go theorems. The first of which is probably very familiar to everyone here, the no-cloning theorem, which deals with the task of taking a single quantum state, putting it through some cloner, which we model as a black box, and outputting two copies of the quantum state. The second no-go theorem is called no-teleportation. And the no-teleportation theorem essentially says states the difficulty of converting a quantum state into a classical message and back to a quantum state. And so we have a quantum state and a deconstruction process that turns it into a classical message, and then a reconstruction process that turns it back into a quantum state. And note that anytime I say teleportation here in this talk, I mean teleportation without entanglement. I know this is there can be a bit of confusion about this, but this is just how what is called in the context of the no-teleportation theorem. Teleportation in this context is teleportation without entanglement. It's just sending a quantum state through a classical channel. So these two no-go theorems are really important, very fundamental to our understanding of quantum information, about what quantum information is and how we can use it. If you ask anybody and their grandma, they will tell you that these are equivalent. And you know, how are they equivalent? They're equivalent in the sense that if you take if you have a quantum state that is clonable, then it is also teleportable. And if you have a quantum state that is teleportable, then specifically it's also clonable. So here in this, so these two are in that sense equivalent. But here in this talk, I'm going to challenge that notion. And specifically, the way that they're equivalent is if you don't consider computational efficiency. And so, how do we see that these two no-go theorems are equivalent? It's by something called a reduction. So we start with assuming that we can do teleportation. So if we can do teleportation, then specifically we have a deconstruction process and a reconstruction process, and then we want to see how to use it to do cloning. And the way to do that is you take the quantum state that you get as input, you pass it through the deconstructor, then you create a classical message, and that classical message can be cloned, of course, because classical information can be cloned. So you pass it through the reconstruction twice independently to get two copies of that quantum state. What about the other direction? What if we're able to do cloning? Does that mean that we can do teleportation? So in this direction it's not as trivial, but you can still do it. And then the way to do that is, suppose you have a cloner, what can you do? So you clone once, twice, 3 times, enough times, as many times as you need in order to be able to do tomography, which gives you a classical description, a full classical description of the quantum state, which of course then you can send over. And then once you have, on the other side of the channel, you have a full classical description of the quantum state, and then of course you can construct it. And so what's wrong with this picture? So if you're a computer scientist, you care about efficiency. And so you might ask, is this efficient? And the answer is no, that in order to be able to do tomography, the number of times that you need a clone in order to be able to do tomography is exponential. And so this reduction specifically isn't efficient, let alone discussing the other parts of the teleportation procedure here. And so you might ask, well, is there a way to make this equivalence efficient? Is there an efficient reduction? And our paper says no. There's no polynomial time black box reduction specifically. And what this means is that unlike to unbounded computation, unlike to unbounded processes, for an efficient observer, these two no-go theorems are not equivalent. And specifically, what what a theorem says is that efficient cloning does not imply efficient teleportation. And specifically that there exists a set of quantum states and quantum oracles relative to which they can be efficiently cloned, but not efficiently teleported. And if you like precision, then we specifically say that they can be that these states can be perfectly efficiently cloned, but you can only teleport them with negligible probability, and you can efficiently clone even in the worst case, but you cannot even teleport in the average case. So how do we do this? Our scheme is as follows. We start with a random oracle, which is essentially just a classical random classical function that starts from a large number of bits m to go to a smaller number of bits n, and we use that to define the set of states psi z, which are just the set of the set of states. So they're superpositions over pre-images of an image of H. And then finally, we have a cloning oracle that clones this set of states. Now, before I get any objections that say, is this cloning oracle unitary? Well, yes, it is, because if you take a look at these at the set of states, you'll notice that these states are orthogonal, and specifically, orthogonal states can be cloned, but maybe not efficiently. So this cloning oracle is a cloning oracle that just abstracts that away and clones these states. And really, what this is this is just a manifestation of this black box that we talked about earlier. Essentially, it gives us a black box for cloning this set of states. And what we want to show is that even given this black box for cloning this set of states, it still doesn't allow us to teleport efficiently. So what we need to do? Is we need to say that if you're given these two oracles, the random oracle and the cloning oracle, then you cannot do the following task. You cannot do teleportation, which is to say that if you sample a random challenge z and the corresponding state psi z, you pass that state through a deconstruction to get a classical message, and through a reconstructor to get a quantum message. You cannot succeed in getting the original state efficiently. Well, so how do we do this? The first thing that we do is a bit counterintuitive. Is we actually strengthen the thing that we want to prove, and what we prove actually is that even if the deconstruction process is unbounded, then we still cannot teleport. And so why do we do this? Why do we strengthen it in this way? Because it kind of simplifies the format of what we need to prove, because what we have now is that this unbounded deconstruction can be just abstracted to an advice string that's given to the reconstruction process. And so now we have something that's a slightly easier format. And so what we want to show now is that given these two oracles, you cannot do this reconstruction. So I want to say that we cannot reconstruct using both this random oracle and this cloning oracle, given this classical advice. And we do this in 3 steps. In the first step, we just completely ignore the cloning oracle. And what we say is that we cannot reconstruct if we just have access to the random oracle. And we do this by a reduction to the hardness of finding multi-collisions. In the second stage, we add a limited version of the cloning oracle, which is a z-cloning oracle, which only clones on the challenge state psi z. And we prove this by a reduction to the previous step by an analysis on the query weights on psi z. And then in the last stage, we add the full cloning oracle. And now we want to show that even with the full cloning oracle, we still cannot do this reconstruction process. And this is the most technically challenging, part of the proof. But roughly speaking, what we do is we show that that if you can reconstruct using this full cloning oracle, then you can also do this with the limited one by simulating by simulating a freshly sampled cloning oracle, and we get it so that it's not a perfect simulation, but it gets close enough to where to where you can still reconstruct using just this limited oracle. And so, what does that tell us? This indicates to us that efficient cloning does not imply efficient teleportation. And this is surprising because this contrasts with the standard understanding or with the information theoretic versions of these tasks, which are equivalent. So unlike the information theoretic tasks, the efficient tasks are not equivalent. And specifically, we have an oracle separation between them. And so one interesting aspect of our proof is that we go through this intermediate step along the way of showing that you cannot do this task of reconstruction given some advice string. And so what you can actually do is you can actually factor it out in its own task that we defined, that's called reconstruction. And so what we actually show in the paper is that efficient cloning does not imply efficient reconstruction. And there's a very trivial reason that if you can teleport, then you can reconstruct. And so this implication is trivial. And if you follow the logic of the arrows, you'll see that these two arrows combine to show that efficient cloning does not imply efficient teleportation. But so this reconstruction task is also interesting in its own right because of the way that it's different from these other two no-go tasks, from cloning and teleportation. Specifically, we can define it like this, but the important thing to note is that this reconstruction task is trivial for efficient adversaries, very much unlike for cloning and for teleportation. And what that means is it only appears when you consider computational bounds. And there's no corresponding no-go theorem. So there's no such thing as a no reconstruction theorem, because for unbounded adversaries it's trivial. So my question and an open problem that I'm posing: are there other such no-go tasks that have not been yet considered up till now, because in the information theoretic world, these are equivalent. Either they're equivalent to no cloning or no teleportation, or in the information theoretic world, they're either trivial or impossible. But where in the computational setting, these become a lot more interesting and a lot more involved. And so let me end with an application, a speculative application. So one thing you might think is, well, so what can I do if I have a state that can be efficiently cloned but not efficiently teleported? And so one possible thing that you might do is something called key non-exfiltration. And the setting is as follows. So suppose that you have a server that's running cryptographic tasks for thousands or millions of clients. And so specifically, it has some secret key. This is classical for now. You want, and so this key is being used to run all these cryptographic tasks for the clients. And specifically what you, and suppose that an adversary was able to infiltrate the system, infiltrate the server. And it's like, say a virus is able to completely take it over. What you want to do is you want to say that you want to have the case where even if the adversary is able to do that, take over the server, that they're still not able to send out the secret key, so that an outside adversary now has the key. So you might think that this is not exactly trivial. That such a thing is possible, but there are some ways to do this even classically. So one construction due to decrescendo, Lipton, and Wallfish. This is very roughly speaking that you have just a very large key, so large that the adversary with its limited bandwidth would not be able to send out the full key before you're able to shut it down, before you're able to catch it, and without being able to send out the full key, the outside adversary has nothing because the full key doesn't give it anything. That's right, the partial key doesn't give it anything. And the problem with this, of course, as you might imagine, is having such a large key that you can get this kind of guarantee means that you have to have a really large key, and a really large key has several limitations. For example, you might be worried about about storage. So say this is a Google server or an Amazon server that runs for thousands or millions of clients every moment. It has large bandwidth of its communication to the outside world, and so have a key that can't possibly be exfiltrated. You have to have a really large key that's going to be very difficult to store, very difficult to do any operations on, because anytime you want to do some operation on the full key, you at least have to read the whole key. So this is a limitation classically. But what can we do if we're in the quantum world? So if we're in the quantum world, then now keep in mind that we're still considering the same cryptographic tasks. The server is still doing the same cryptographic tasks for its clients, and so specifically that means that the communication with the outside world is still classical. But now we allow the server itself to be quantum, so it can do quantum operations on the server. And so, if you're able to encode the key into a clonable but not teleportable state, then what you could do is you can clone it as many times as you want on the server, so that you can specifically do run these cryptographic tasks in parallel. So suppose you have thousands of clients all making queries at the same time. You can run them in parallel. You can use this key in parallel over many parallel processes. But despite that, if an adversary were to take over the system, if an adversary were able to infiltrate the system, they still can't exfiltrate the state, exfiltrate the key, because of the no-teleportation property. And so another open problem that I'm posing is to specifically give a plausible construction for this cryptographic primitive, for this new cryptographic primitive that we propose, that allows you to do this under some, say, standard computational assumptions, or anything that can give you a plausible real-world implementation. And so now I'll leave you guys with this cat that's for unfortunate reasons decided to try to run through our statement, our thesis statement, and it didn't end very well for the cat. So thank you.
Question.
Thank you for interesting talk. So it might be stupid question, but so please go back to the implication slide. So slide about implication. Yes, I can understand the figure. So, but is there any possibility we can the teleportation is available from quantum state to quantum state by using cloning, efficient cloning oracle efficiently. So so in my understanding, you show that the impossibility by teleporting quantum state to classical discretization to quantum state. So, but. So, in my understanding, you can show that the impossibility by teleporting quantum state to classical discretization to quantum state. So, but. So, in my understanding, you can show that the impossibility by teleporting quantum state to classical discretization to quantum state. So, but. So, in my understanding, you can show that the impossibility by teleporting quantum state to classical discretization to quantum state. So, but. So, in my understanding, you can show that the impossibility by teleporting quantum state to classical discretization to quantum state. So, but. So, in my understanding, you can show that the impossibility by teleporting quantum state to classical discretization to quantum state. So, but. So, in my understanding, you can show that the impossibility by teleporting quantum state to classical discretization to quantum state. So, but. So, in my understanding, you can show that the impossibility by teleporting quantum state to classical discretization to quantum state. So, but. So, in my understanding, you can show that the impossibility by tele So you can show you can deny such a possibility from directly quantum state to quantum state.
So the definition of cloning is the definition of teleportation is specifically sending a quantum state through a classical channel. And so that's what it means to like go from quantum to classical to quantum.
So in this paper, the definition is such a thing. So how about the first question? So quantum to directly quantum to quantum. So such a teleportation is also impossible efficiently.
I'm not 100% sure I understand what you're saying, but maybe if you want to talk after the offline, we can discuss.
Thank you.
Hello. Thank you for a very nice presentation. Would you be able to say anything about how this relates to the QMA-QCMA class distinction or the complexity of describing ground states? Is there any implication here?
That's a really great question, and it's something I've been thinking about, but I don't have any specific results right now. There's a difference in that these tasks are mainly to output a quantum state in most of them, whereas QCMA and QMA are all like deciding a classical language, but there may be some implications, and if there's anybody who is interested in exploring that, please talk to me.
Oh, hi. So thank you for the nice talk. And I think the result of the impossibility for the non-key exfiltration not only applies to the adversary, but also to clients living outside of the server room. So, for example, even if you have multiple copies of the same key, if you want to use it like in a communication with the clients outside of your server room, then you still have to classically, communicate the measurement outcome of your keys to your clients. But because of this property, I think that you still cannot have efficient communication of of that data with the clients, even if they are not adversaries. So what's the usage of these efficiently clonable states when they are not efficiently teleportable?
Yeah. So what this construction would do, this is of course a speculative construction, but what it would do is it would be some cryptographic quantum cryptographic key for a classical cryptographic task. So essentially, client would send in a classical query, and it would receive a classical answer, and the key would stay on the server. So all the clients would access the server through a classical message, and that would send out classical output. And yes, the non-teleportation of the key means that the client will never be able to see the key, but the client doesn't need to see the key; just queries the server, just asks questions of the server. Does that make sense?
Okay, there's one question here.
Hello, thanks a lot for your talk. Maybe I'm interpreting things incorrectly, but when I guess I'm wondering, for me, a clonable state strikes me as one that's sort of classically describable, in which case it doesn't necessarily, to me, the black box model doesn't necessarily make a lot of sense, because if you can, it almost seems like you're forcing your algorithm to learn the form of the state and then to produce it. Whereas, I mean, can you say anything about this, the difficulty of this in sort of a glass box model where you're given a description of the circuit that produces your clonable state?
Yeah, so of course, this is a good point that the separation that we show here is only a black box separation. There may be other. It doesn't preclude the existence of non-black box reductions, but there is some sense in which cloning is not a classical is not necessarily a classical operation, because you might think about ways in which, for example, there's a quantum state that is sort of divided among the two copies, right? So there's no sense in which the quantum state turns into a classical description as the part of the cloning process.
But you wouldn't say like the clonable state is at least classically readable somehow, or I'm not very familiar with this. But is that?
Yeah, so I think this result is giving evidence to the fact that that's not necessarily the case, I think.
There's multiple more questions, but I'll take just one last question, and then we'll take the rest for coffee.
Thank you very much. So I have a question. Like usually, this kind of setting we consider like a part of maximum entangled state to put to the unknown state.
I'm sorry. Can you put your microphone closer?
Sorry, the unknown entangled state. So this state is entangled to something out there, and then teleport is kind of keeping entanglement to the other side. Right, this state here is can be secretly entangled to the outside world. So in this case, if you consider like a cloning, is how do we should understand this cloning? If it's kind of secretly that this state is secretly entangled to other outside.
Yeah, so that's a good question. So. So in this paper, what we consider is if it's entangled with some outside state, then we just consider the density matrix, the local density matrix, and we want the output to be a state that has the same density matrix, or at least a similar enough density matrix. But I understand that doesn't fully capture the case of being entangled with the outside, but yeah, that could be a follow-up work.
It looks kind of impossible to keep the entanglement anyway with this classical, if no entanglement allowed. So it's kind of it's clear it's a difference of the cloning and teleportation in the sense, no?
Yeah, there might be something to that.
Okay, let's take our remaining questions over coffee and thank the speaker.